Continuing on Physical Chemistry, Chapter 3, we're beginning Section 5 now. We're going to be talking about entropy as it pertains to reversibility and irreversibility. Now first, let's talk about reversibility. Then the change in entropy is just the change in entropy of the system. Now remember, the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. Now here's our system. It's surrounded by walls. Then the surroundings. All of that together is the universe. So let's say we have heat going into the system. That's positive dq, differential of q. Now the differential of the entropy of the universe is equal to the differential of the S of the system plus the differential of the entropy of the surroundings. So that's equal to the differential of the heat reversible divided by temperature plus negative Q reversible over temperature. Now since, remember, if you have heat flowing, the heat going into the system has to be the same as the heat coming out of the surroundings. So that's why this dq here for the system is equal to the minus dq reversible for the surroundings. Except remember, from the system's point of view, if heat's coming in, it's positive, and from the surroundings point of view, if entropy is going in the heat is going into the system, then it's minus. That's why we have positive here, minus here. Since it's the same, this plus this cancels out, it's equal to 0. So that means that the change in entropy of the universe is equal to 0 for a reversible process. Now remember, the entropy of the system plus the entropy of the surroundings is equal to the entropy of the universe. What this tells us then is that for a reversible process, the entropy of the universe must remain constant. Now remember, entropy, internal energy, enthalpy, Gibbs free energy. Well, actually we haven't talked about Gibbs free energy yet, but it's a type of energy, and these are all state functions. Now remember, if you have a derivative such as the partial derivative of x with respect to y with respect to z, that's the same as 1 over the partial derivative of x with respect to y with respect to x holding z constant. I think I said that wrong. This z means constant z. Now remember, for an ideal gas, PV equals nRT. Also remember from your, I think it was trigonometry, where you learned sine squared of alpha plus cosine squared of alpha is equal to 1. Now these not particularly relevant right now, but we're going to be using these later on when we do certain calculations. And of course this alpha here is any angle. And then we have T2 over T1 is equal to V1 over V2 to the power of R over the molar heat capacity constant volume. This is for an adiabatic process. And then gamma, we defined that earlier. So P1 times V1 to the gamma is equal to P2 times V2 to the gamma. Remember, P is pressure, V1 is gamma. P is pressure, V is volume. And that's only for an adiabatic process, of course. Now let's talk about an irreversible process, an adiabatic one. So here we have a graph of pressure versus volume. We're going from state 1 to state 2. Instead of drawing a line, we're just sort of drawing swigglies to show that it's not reversible. So we're going to do this in a finite number of steps. That's one way to make it irreversible. Once we get to state 2, we can't get back to state 1. So that's why these are arrows pointing from state 1 to state 2. So just like we did before with the phase change of supercooled water to ice, we're going to create a reversible path as an alternative. So here we are. From state 1, we're going to do an adiabatic expansion. Then we'll do an isothermal expansion. And then we'll do a reversible adiabatic compression. Except I had that backwards. So we're actually going to go back from state 2 to state 1. So we're going to do a reversible adiabatic compression, an isothermal compression, and then an adiabatic expansion. And remember, this is pressure against volume. So HR is for hot reservoir or heat reservoir. So this is T subscript HR is the temperature of the heat reservoir or the hot reservoir. So like I said, step 2 to 3 is adiabatic and reversible. Step 3 to 4 is isothermal and reversible. And step 4 back to 1 is adiabatic and reversible. Now remember, entropy is a state function. So entropy at state 2 minus the entropy at state 1 is equal to the change in the entropy of the system, irreversible. But what is that? Well, remember, the change in entropy from state 2 to 3 is equal to 0 because it's adiabatic. So Q reversible is equal to 0. So that means the entropy at state 3 minus the entropy at state 2 has to be equal to 0. Therefore, the entropy at state 3 is equal to the entropy at state 2. So remember the diagram. We just showed that the entropy here is equal to the entropy up here. Now, going from state 3 to 4, we're going to let heat out to maintain constant temperature. But we're also going to get entropy to state 4 so we can match state 1. So the entropy of state 4 minus the entropy of state 1 is going to be the definite integral from state 3 to state 4 of dq reversible over temperature is equal to 1 over the temperature of the hot reservoir. Remember, that's on the diagram. I didn't explicitly say that, but we have a hot reservoir up here. Times the entropy from state 3 to state 4 of dq reversible, and that's just going to be the heat from step 3 to 4 over the temperature of the hot reservoir. So remember, that's an isotherm going from step 3 to 4 at the temperature of the hot reservoir. From step 2 to 3, the temperature was actually rising because we were compressing the system. Now this is not a Carnot cycle. It may look like it from the diagram, but 1 to 2 is irreversible. In a Carnot cycle, all 4 steps are reversible. So anyway, the cyclic integral of the differential of the entropy of the system is equal to just the entropy at state 2 minus state 1, plus the entropy at state 3 minus the entropy at state 2, plus the entropy at state 4 minus the entropy at state 3, plus the entropy at state 1 minus the entropy at state 4. You'll notice all those cancel out, so even if you didn't know anything about entropy, you should be able to figure out algebraically it's got to be equal to 0. Now we already said S3 minus S2 is equal to 0, and S1 minus S4 is equal to 0. So, because those two steps are adiabatic and reversible. So that gives us that the cyclic integral of the differential of the entropy of the system is equal to the entropy of state 2 minus the entropy of state 1 plus the entropy of state 4 minus the entropy of state 3. And that has to be equal to 0 because we have a cyclic process. So we have the integral of, we have the entropy at state 2 minus the entropy at state 1 plus the heat going from step 3 to 4 over THR, the temperature of the hot reservoir. That's equal to 0. So we have the entropy at state 2 minus the entropy at state 1, move this over, is equal to minus the heat from step 3 to 4 over the temperature of the hot reservoir. Now we know the cyclic integral of the differential of internal energy is equal to 0 because it's a state function. So the cyclic integral of dq plus dw is equal to 0. So the cyclic integral of dq plus the cyclic integral of dw is equal to 0. So the cyclic integral of dq, remember, is q3 to 4. So q3 to 4 plus w is equal to 0. Therefore, the work has got to be equal to minus the heat from step 3 to 4. Now remember, by our nomenclature, work is the total work done on the system. In this case, the work means all the steps put together, but it happens to be equal to that one step, q3 to 4. So like I said, positive work means energy going into the system, minus work means work is being done by the system. Energy is coming out of the system via work. Now suppose that q3 to 4 is greater than 0. Then the minus work is greater than 0 and work is less than 0. This is a violation of the second law, which is impossible. Now suppose that q3 to 4 is equal to 0. Well, then no work is done. That means q3 to 4 is equal to 0, work equals 0, so dv equals 0, which means 0.3 and 4 are the same point, which is impossible unless, of course, your system has actually just sat there doing absolutely nothing. But that wouldn't be a reversible case, now would it? It wouldn't match the diagram. So let's try the third alternative. Suppose that the heat from step 3 to 4 is less than 0, because it's the only choice left. Then the entropy from state 2 to state 1 is greater than 0, and the change in the entropy of the system is greater than 0. So we can conclude now that the change in entropy of the system is greater than 0 for an irreversible, adiabatic, closed system. Now the entropy of a closed system must increase in an irreversible adiabatic process. That's a rewording of the same thing I just said. But what about a reversible adiabatic process? Well, then the change in entropy of the system is equal to 0 because dq reversible is equal to 0. Now for a reversible isothermal process, the change in entropy of the system is less than 0 if Q is less than 0, or the change in entropy of the system is greater than 0 if the heat transfer is greater than 0. Now if we have an isolated system, the change in entropy of the system is greater than 0. But that's if it's irreversible, adiabatic, and isolated. Now remember, the change in entropy of the system plus the change in entropy of the surroundings is equal to the change in entropy of the universe, which is greater than 0 if it's an irreversible process in an adiabatic system. Now remember, the change in entropy of the system, or the surroundings, is going to be equal to 0 if the system is isolated. So what this tells us then is that because, remember, a reversible process is an idealization. Real processes are always irreversible. Therefore, the entropy of the universe is constantly increasing. So remember, the change in entropy of the universe is equal to 0 if you have a reversible adiabatic process. The change in entropy of the universe is greater than 0 if you have an irreversible adiabatic process. Well, that's an ugly A, isn't it? Looks like an N. Adiabatic. So the change in entropy of the universe is greater than or equal to 0 for any process. Notice that the change in entropy of the universe being less than or equal to 0 is not one of the choices. It can't happen. Now entropy can be created but not destroyed. So entropy is not a form of energy. There is no such thing as a conservation of entropy. It can be created out of nowhere. And in fact, an irreversible process will create entropy or increase entropy. So the second law says that the dq reversible over temperature is the differential of a state function, entropy, such that the change in entropy of the universe is greater than or equal to 0 for any process. We mentioned that at the beginning of section 3, but now we've mathematically, maybe not proven it, but shown that. So remember, like I said, reversible is an idealization. It doesn't happen in real life. An irreversible process, that is a real process. Now one thing that's interesting, entropy is time's arrow. It's time, positive time, is always pointing towards maximum entropy. Now let's talk about entropy and equilibrium. Let's say you start out with a system. One side's at T2 and one side's at T1. That's temperature. Capital T is temperature. And we're going to just say that, okay, this temperature on this side is higher than the temperature on this side. So here's a graph of entropy versus time. Lowercase t is time. Capital S is entropy. What's going to happen then, over time, the entropy is going to increase, but it's going to level out. When it gets completely flat, you're at thermal equilibrium, which means the two temperatures will be the same. For example, let's say you have hydrogen gas and oxygen gas in equilibrium with water gas. So I guess you'd call it water vapor, actually. There's a couple things about this equation. One, thermodynamics can't explain how fast we reach equilibrium. I mean, it might take 10 minutes, it might take 10 years, it might never happen. You wouldn't know from thermodynamics. Same with graphite, diamond, carbon. So at room temperature, normal pressure, graphite is actually more stable than diamond. So if the universe were at equilibrium, you would expect all the carbon at room temperature to be graphite. But again, we can't tell you how fast that's going to happen from just thermodynamics. Later on, we will talk about that. And this is the end of section 5.